Epipolar restriction. The epipolar geometry is the intrinsic projective geometry between two views. The application of projective geometry techniques in computer vision is most notable in the stereo vision problem, which is very closely related to structure from motion. Unlike general motion, stereo vision assumes that there are only two shots of the scene. In principle, then, one could apply stereo vision algorithms to a structure from motion task. Applying projective geometry to stereo vision is not new and can be traced back from 19th century photogrammetry to work in the late 60s by Thomson, E. Thomson, 1968. However, interest in the subject was recently rekindled in the computer vision community thanks to important works in projective invariance and reconstruction by Fogaras, O. Fogaras, 1992, and Hartley, R. Hartley, R. Gupta, and T. Chang, 1992. Epipolar restriction is independent of scene structure, and only depends on the camera's internal parameters and relative pose. The epipolar geometry between two views is essentially the geometry of the intersection of the image planes with a pencil of planes having the baseline as axis. The baseline is the line joining the camera centers. This geometry is usually motivated by considering the search for corresponding points in stereo matching, and this explanation will start from that objective here. Epipolar restriction. Suppose that a point x in a third-dimensional space is imaged in two views, C, at x in the first, and x in the second one. The relation between both points is inherent to the scene and can be seen in. As shown in the image, points x and x, space point x, and camera centers are coplanar, denote this plane as pi. Clearly, the rays back projected from x and x intersect at x, and the rays are coplanar, lying in pi. This latter property is the one that is of most significance in searching for a correspondence. Suppose now that x is the only known point, it can be determined how the corresponding point x is constrained. The plane pi is determined by the baseline and the ray determined by x. From above it is known that the ray corresponding to the unknown point x lies in pi, hence the point x lies on the line of intersection L of pi with the second image plane. This line L is the image in the second view of the ray back projected from x. In terms of a stereo correspondence algorithm, the benefit is that the search for the point corresponding to x need not cover the entire image plane but can be restricted to the line L. These lines are known as epipolar lines. So the matching problem is reduced to seek for the corresponding point, not in the whole image, but only in those points lying on the epipolar line of the other camera. The linear epipolar geometry formulation also exhibits sensitivity to noise, i.e. in the 2D image measurements, when compared to nonlinear modeling approaches. One reason is that each point can be corresponded to any point along the epipolar line in the other image. Thus, the noise properties in the image are not isotropic, with noise along the epipolar line remaining completely unpenalized. Thus, solutions tend to produce high residual errors along the epipolar lines and poor reconstruction. Experimental verification of this can be found in the references, A.J. Azerbaijani, 1997. After the epipolar restriction has been detailed, this work will continue with the general matching problem. Next, before the discussion of the matching process problems and the application to neuromorphic engineering, a global classification of the matching algorithms will be shown.